This is just a quick presentation on the Baggins Road Deviation project to the Shire Regional Council members. I'd like to thank Mayor Gandorf, Deputy Mayor Soron, Councillors Gamgee, Golem and Oakenshield for your time today. I'd also like to acknowledge the team that assisted with this, primarily Ken Russell for the information supplied in this, preparing this. So here we see the God, I hate this thing. So here we see the general layout of the project. Note the poor alignment of the existing blue road, and we'll see improving of the alignment on the red road. The range of the swamp wallabies is indicated in pink, and the locations of the various features are included in the project. So there. Water management is a key aspect of any project, especially a build. The culverts that we're going to install will allow water to flow from one side of an embankment to the other, underneath the embankment, and typically over small creeks and low points. Care has to be taken when water flows so that the water flows well away from the road so that the road isn't damaged. Water is not a road's friend. And when the water is carried off, that sediment contained within it is actually dropped out of the watercourses of these water flows before it reaches waterways. Here we see 3 examples in Bolton 2. Water control is not something just done once off. It has to be done at the start and right the way through the project. Here we see erosion control happening whilst we're constructing. On the picked left, we see a simple drain to a collection point where a sump is constructed to drop out sediment before it's evacuated into the environment. And picture right, we're actually seeing this is a GF membrane, but synthetic layers to use to basically prevent water egress into layers underneath or to stop water rising up through capillary action into your road base, causing damage. It's a really effective tool. Here's some examples of some successful water control measures, but there are some issues due to poor management, which is the key with these. So pick left shows us some sandbanks that were working effectively, but they'll move to allow some movement of some plant through the area, and you're actually seeing where now the sediment that had dropped out has now been able to enter the stormwater system, which is something we didn't want to see. And picture right, you're actually seeing a successful deployment of a sediment fence. The curious thing to note is, to the closest to the picture, you're seeing where the sediments have flowed into the gutter and has started to flow into the road, but there's no sediment flow. Technology actually works. Now, this is just some more examples of successful water controls that were employed during and after an event. So picture left shows the jute sausage or the jute fibre sausage that we see everywhere. It's been successful. It's blocked a whole heap of sediment, and you can actually see the point where it's actually now become part of the environment. You can really make it out because of the survey pegs holding it into position, and it's got grass growing it to further help stop sediment, which can become another issue in itself if not managed. And pictures right, you're actually seeing 2 completed situations where another temporary sediment control measure has dropped out some quite coarse sediments into before they've reached a drain point. And picture right lower, you're actually seeing a well completed drain where they've used coarse faced concrete to help slow water rapidity so that it doesn't tear into the Blackmans Creek at the bottom. And it's slowing down and is an effective. When you need to treat a larger area of I suppose terrain for scout protection, we can employ basically rock armouring or riprap to slow down the water speeds and velocity across the surface and thus reduce scour and help drop out sediment. So picture left, you're seeing where a large-scale slope is protected basically by ballast down into a toe protection of the slope. And picture right, you're seeing a culvert that is draining one side of the road into a watercourse, a semi, a not full-time watercourse, and it's using the rock armature. Now, when we're about to, so now we're moving on to construction and excavation. So part of the excavation process is we're using empirical methods to try and estimate how we are going to approach our digging. Now, so these inferences are not guaranteed, but they're certainly a good start. And we can thus estimate the diggability based upon the symbiosis and Soroglue, which is the top left picture. That's based on a visual method. Then you've also got Pettifer and Fuchs, which is the upper and right, which is requires a little bit more geological data, but you can balance it and try and estimate your digging methods based on those. And then you can use those to select your machinery, and then you can then estimate your digging and ripping rates and your productivity rates from other various sources. In this case here, we've got Methven Software and the Wyoming Department of Transport, where they're showing some productivity charts. And a lot of these machinery suppliers actually have these parts out there, the charts, and we're using those to actually give ourselves a better chance. Now, more empirical estimation. This one here we're using to assess the embankment construction, and this figure is the Australian Guide to Pavement Technology Part 2. Really shows it's built on a vast array of knowledge in Australia and New Zealand, and it's a really good way of just saying how much cover for your traffic do you need to ensure that your road is working well or should perform. And the information that we have based upon the existing road and was supplied shows that this project should be successful, and we think, son of a bitch. So here we, this is retarded. So we now have the situation where we've got a successful design. We know the design is engineering correct. We've got some parameters. With regards to methods of building, the way we can build things is, first up, is with scrapers. Now, scrapers are kind of self-contained dig, transport, dump machines. They're quite versatile in a lot of respects. They're quite quick. They really can power down slopes and excavate quite rapidly, but they do require a bit of highly skilled operator levels. And you can see here a couple of scrapers doing push pulling, which improves productivity by scraper 1 loading its hopper or the bin, and scraper 2 pushing it, and then scraper 1 will then pull scraper 2 whilst it loads its bin, and they can disgorge at the same sort of rates. It's a very effective way of excavating and constructing embankments. It's particularly effective. The next method of construction that we're going to look at is the typical load and haul, and this is seen the world over and it's quite familiar. You've got loaders, backhoes or excavators, as you see in the top pictures here. They basically load the fill into the tubs of the trucks. The trucks travel down quite serviceable roads or some serviceable temporary roads, unload the fill into the project where you're basically your graders and your rollers and whatever else spread it and compact to the specifications. An advantage with these machinery or this construction method is your machinery is incredibly versatile. You can use your tippers for moving stuff, moving plant around site, moving everything else around site. You can use your excavators for low intensity craneage if you require. Thus, you can see this excavator in the bottom is being used to build and install some culverts behind a pile wall, which is incredibly helpful in basically getting or keeping your And last but not least, and it's certainly an interesting one, is a dozer push construction method. Now, this is a very short method of construction. Typically, it's most effective in a transverse cut and fill scenario where we've got a cutting and we use the dozer to dig into the face and push into the fill slope. That's what you're seeing with this dozer in the picture right there. And it's a good system, but it really, once you've exhausted your short fill, it really becomes a case of it's so part of the construction method obviously is appropriate compaction. Now, again, more empirical basis for the assessment for the design here is, or for construction, is Ostrodes. Now, they've actually provided us with this table where it basically provides the roller type with the material type. So heavy clays, you use your the center picks, which is the padfoot roller, and the pneumatic tied roller. For sandy clay, you're still using the same machinery. They're very efficient machines. For crushed rock, you want the same two rollers, but you also want to then think about a smooth drum as part of that, a vibrating smooth drum, to get that energy and to get the compaction happening. If you're using fill, however, you want to use the grid roller and the impact rollers, which are the bottom left and the upper right pictures. Very effective at dealing with those larger block sizes and breaking those and compacting those larger rocks into a more stable base. The steam roller at the bottom is of course predominantly used by hipsters and vintage machinery enthusiasts. I'll let you think about whether we want to use that here at the Shire Council. Now, the degraded granites of the Moira mine are estimated to behave similarly to a sandy gravelly clay. Thus, we're expecting that smooth drums and vibrating drums will be needed for the select material zone under the base. The embankment fill will require a grid or compacting roller because we're expecting to see those larger folds. And we'll also need a pneumatic tied rollers will be needed for the base construction. An important point, I suppose, with these rollers is the homogeneity of the fill. There's a huge problem with large rocks in those fill, especially on the smooth drum rollers. The moment it will basically take all that point loading that the rollers will give, and it'll take it and put it into one little section. You get a weak spot in your road. So those sections must. Now, the embankment construction does require safety barriers to basically ensure the safe transit of the vehicles and they don't run off into quite a significant fall. We've got a few options, and concrete barriers are protecting, you can see here, protecting the bridge. They're basically very strong, they're very durable with little ongoing maintenance, but they're higher expense cost, and when they are damaged, they're a massive headache to repair. The steel barriers, which you can see in basically the upper left and to the left of the bridge photo, bridge abutment, they're strong, they're quite strong, and they're quite visible, and they have really good crash resistance, but damage is not easily repaired, and it can be quite a major task to repair them if they are damaged. The wire ropes, which you're seeing in the center bottom picture, they're quite cheap, they're relatively cheap to roll out. They're relatively cheap to repair because if a car hits them, all you have to do is replace those HDPE, high density polyethylene risers, and the barriers are back up and running. The problem is when those barriers they're impinged, they can actually present a bit of a hazard themselves in the fact that they won't stop vehicles. So that is an issue with regard selection. Neither wire rope nor the steel beams allow pooling of cool air or moisture behind them. So they actually, in a cooler climate like we're in, they are the preferred option over the concrete barriers. And in this case here, we're recommending that council adopt. And the project will require the construction of deceleration and wait lanes so that vehicles can enter the car parking. So we've got two options here. One is the auxiliary lefts treatment, which you're seeing in the picture left, which is a designed deceleration lane so that vehicles traveling effectively southbound can safely pull off to the left and enter the car park without sort of impacting on or fear of being rear-ended. The converse, and you're seeing that picture right, is where you're seeing vehicles being given a small turning treatment in order to allow them to enter the car parks safely and basically wait on the road without impacting on travel, and giving perhaps inattentive drivers who are coming from the rear the chance to avoid a rear end accident by heading off to the left. Now, this is all guided by the Austroads Guide to Unsignalised and Signalised Intersections. The sight distances on the design appear that we don't necessarily, and the speed that we don't. So the next part of the project I'd like to talk about is the fauna management aspect. So as we're aware, the swamp wallabies are here. We will need signage to warn road users that they are in this area. They must conform to standards Australia designs. It's really important. The thing is, I suppose, the reality is of where we are is the remnant vegetation is an important habitat for native animals, and we have to manage it accordingly. We really can't put the road in any different manners to avoid this issue. So unfortunately, we have to put the road through this. Regarding the first thing of moving these animals from one side of the road to the other, there's a couple of preferred options. Basically, you've got a couple of options. One is an underpass and one is an overpass. The overpass is the preferred option, but it's a lot more expensive as it's a lot larger. But there's a lot of literature that says an underpass, when it's done correctly, will actually provide a lot of access. And you see that on the left side photo, where you're seeing, again, human for scale, as is common in geotechnical presentations. You're seeing a culvert that's been fenced off to encourage native animals to use this culvert as a transit point. Certainly, that's a very good way. So with regards to the Baggins Road project, we've actually been doing a lot of research, and the Vic Road guidelines are a really good start point for how to manage your interactions with your animals. And they've basically hit the macropods being kangaroos and wallabies. They've given us straight guidelines as to what's acceptable, and even they've been using them themselves. So what we're going to propose is that we have a large scale mammal culvert that will allow the animals to run through. We don't have a very wide road, so a single culvert should be acceptable. Certainly not the bridge that's pictured in picture left, but we are also going to put some fencing along the roads to dissuade the animals from entering that road in some of the kill death zones, especially around the corners. And the key point is we're going to actually have to landscape these culverts so that they're effective in excluding the animals from the danger zone. So regarding project planning and sequencing, the key points are that this design and accuracy right the way through the project allows for the best results. But the key points are culverts need to be constructed well in advance of the embankment. Basically, the delays will kick on very badly. There's some ability to mitigate these delays by starting construction in other segments of the project, but survey control is a key to appropriate clearance of the areas under the design, so we're not clearing too much. And we're also going to use GPS controlled equipment, which basically requires good accurate survey control as well. So now this please note the colours are just purely to help identify tasks. They don't represent something. I'd like to thank Council for supplying us with this brand new planning project. I believe it's something called MSXL. It's an awesome package and it's been doing really well. The idea about planning is it allows us to plan for known events and make the most of them and plan around them. A good example here you can see is the Christmas shutdown period, which is a big purple blob in the middle of the. This allows us the engineering documentation to be completed before, and we can then stagger the construction after the shutdown so that we don't expect our contractors to turn up first day and be trying to do a whole. The next slide we're seeing here, this shows the interdependency of the timings. The upper section shows the critical steps being the cutting, excavation, the culvert installations. Changes 15 to 2,000 and a portion of 1,000 to 1,500 have the potential to be built in advance of lower changes, as do the car parking accesses and the car parks themselves. Thus, if we do hit blockages, we can then keep production going of the project by moving those lower priority projects and thus still being able to estimate we still. Here's a couple of real world examples of how you can simply track the progress of a project. It doesn't have to be done electronically. This is on the back of the crib room wall and it works really well. The priority projects are highlighted to ensure that the schedule is adhered to in the project. See the project met. You can just see where they've actually worked away around a couple of standbys, which is breakdowns effectively. And in picture right, you're seeing where they can priority placements for a section of an embankment build to make sure they're getting the differential settlements, the different placements all done correctly. And it's a really simple way, and it speaks really well to the operators out there, and they need to get the task completed. They can actually do it quite well. The benefits of the thoroughly thought out project, proper planning prevents poor performance. We're using the most efficient use of our available resources. We get quicker constructions. We highlight key tasks where the focus needs to be put on, but it requires discipline. It requires appropriate resources, and it requires daily management. You can't set and forget this. And it provides a great outcome, and I can't suggest that enough. I actually think this is going to be a really good project. I think it'll be successful, Council. I'd like to thank all present for attending today and giving me the chance to express it. Thank you very much.